Okay, well, we got test on the series. We'll talk about that. Actually,
How many problems?
we started out with sequences. We will mention that as well. There are 13 problems, and as usual, you'll be allowed one sheet of paper, front and back. So write down whatever you can, whatever you need to. Help me, Jesus. Oh. Now, we did begin this unit with sequences, so there may be one, probably of the 13, probably just one, but something dealing with sequences. Maybe list out terms. That was one main concept, or find the limit. So the difference, remember, notation, sequence is just A sub n, and then you have your formula. Then the next section we looked at series, which was our nice little, I could never do those very good, but the capital epsilon is what it is, the series notation. And that's basically, we kind of look at this as the sequence term, and then we're adding all of the terms together rather than just listing out like we talked about with the sequence. So don't forget about the sequence. Don't turn it into a series. But okay, now once we get into the series, it's going to be basically, here's a bunch of series, figure out whether they converge or diverge. Okay. And, well, actually there will be a few that say, well, let me back up again, back up just slightly. I can't remember exactly how I put it, but let's see, not show, but state the test used. And show why the series converges or diverges. It's not just going to be, does it converge, does it diverge? I want more than a 50-50 shot at it. So, but definitely state the test, because there will be some series that there might be 4 or 5 different tests that work to show whether it converges or diverges. So the 4 of you, I may have 4 different approaches for one problem. I doubt it, but I could. But anyway, some of them aren't quite as straightforward and obvious which test to use. So especially when you get to some with the comparisons, but now a few of the problems after the state the test and see whether it converges or diverges, there will be a few problems. If it converges, find the sum, or find what it converges to. What series, what type of series did we have those problems for?
Geometric, those problems.
Okay, definitely. Geometric and the telescoping. And sometimes what you have to do with the telescoping, actually, to get it into a form where it's telescoping. Okay, so look for, maybe the first step is going through partial fractions before it gets into the telescoping form. Okay, so recognize that. But yeah, these two are the types that we can find. If it's convergent, we can find exactly what it converges to. And the geometric, now whether it's n equal 1 or n equals 0, that will make a slight difference. Not much, but actually, I think the more common form was n equals 0. This will be a little easier to fit to the equation. We have that. What is the series? What does the series converge to? Do you remember the formula?
So 1 over A, 1 minus A, right?
Yeah, A over quantity 1 minus R. Now, again, that would be if n equals 0. A would be that first R to the 0 power. That's a good way to check what is your first term. So make sure you kind of keep that straight. If it's n equals 0 or n equal 1, you got to watch what would A equal in those cases. Okay?
If it's 1, it'll be AR, right?
Yep. And let's see. This would converge if what?
Oh, it's as R is less than 1.
Okay. In between -1 and 1. We normally look at positive values of R, but it could be like -1/2 to the n power. So as long as R is in between -1 and 1, it will converge. A negative on there, we could go kind of to the alternating series, although we hadn't looked at that one yet, but that's the idea with, if R turns out to be negative, it really is just an alternating series. But this is kind of a quick approach to it. Okay. So geometric and telescoping, make sure you know the details of that, and especially find the sum, not just say whether it converges or diverges. Okay, now the rest of them, we don't know what it converges to exactly. We'll actually look at some of that stuff next week. This is the end of the chapter in Think Well that we haven't covered yet. Those are great problems, but they're not very good problems for tests. So that's why we kind of save that for later. But we will be seeing where some of these converge exactly to maybe e squared or something like that. So give you something to look forward to. Okay. Okay, so the next part, a majority of the test will fall under this, where state the test used and show whether it converges and diverges, show all the details to it. But what are the other tests that we looked at? Okay, P-series.
Limit comparison. Integral test.
Okay, limit comparison.
Direct.
Direct comparison. Yeah, we have several to
Quickie test.
list out. Quickie test. as he calls it, or a little more formal, nth term test.
Oh yeah.
But quickie test is fine. I'll know what you're talking about, especially if I see the work that I should see. Let's see. Somebody said integral test, integral, root, ratio. Now the alternating series. Don't forget that one. Now, with this list of tests, what I would do is kind of set up a list of priorities. Which ones are the easy ones? That's what you want to check first. It's not necessarily the ones we did in order of what we looked at, but definitely, well, that, if that works, then we're pretty much done real quick. The problem with the quickie test or the nth term test, if the limit equals 0, it doesn't tell us anything. But if it's equal to something other than 0, it diverges and we're done. So that's a quick one. Well, that's why he calls it quickie. Also, the p-series, definitely, if you recognize it is in the p-series form, that's a very quick and easy one to figure out. What is the test for that?
It's greater than 1, it converges.
Okay, if you have 1 over n to the p, if p is greater than 1, converges. P is less than or equal to 1, it will diverge. Okay, so that if you can remember that, that's so those two pretty straightforward. Then from here, it's kind of personal preference. I think all of us would agree these first two are what we look for first. And don't forget these. Those may or may not show up again in this section. Those first two will definitely show up in the if it converges, find its sum, because it is possible to find those sums. But keep those in mind for these others, the list of series. But at this point, yeah, it's kind of, well, what does, if it's not one of the easy ones, what does it fit? And definitely the root ones are pretty obvious when to use it. If everything is to the n power, then use the root test. Ratio test, that one, it's not too bad to use, but that one typically is, do we have n factorial, or is there a factorial in it, along with 2 to the n, or something like that. That would be a good time to use the ratio. Okay, and again, you don't have to use the ratio if you're more comfortable with one of the others. The two that are the most diverse would be the comparison tests. Now, sometimes they get a little involved, especially the direct comparison. Some of those you probably thought, well, let's use the direct comparison, and you write it out. It's easy to find something to compare to, but then the condition doesn't work. If you need your series to be less than the one given, well, it turns out to be greater than, that test doesn't work. So over the years, I've found that I like the direct comparison less and less. I'll go with the limit comparison more often than the direct comparison. That's, again, my personal opinion. Definitely, if there's sine or cosine, probably going to be dealing with a comparison. Sine n over n. Well, we can't deal with sine n over n directly. You got to compare it, probably compare that one to 1 over n somehow. And those usually, direct comparison's pretty good because sine n is going to be less than or equal to 1. Cosine n is going to be less than or equal to 1. So those fit nicely into the direct. But there are some combinations where the direct doesn't work real good.
Wouldn't sine and cosine stay between 1 and negative?
Yep. Yeah, between 1 and negative 1. But definitely,
So then how would you, so
well,
what if you take the limit, if you take the limit comparison? If you take
limit
the limit
the-
of sine, what would it be?
the problem with the limit comparison would be limit of sine n as n approaches infinity doesn't exist. And the limit comparison test says L has to exist. Okay, remember we talked about that?
Yeah.
It can't go to infinity. It has to be a particular value greater than 0, but it has to exist. So once in a while, the limit comparison doesn't work because of that. So if that happens, then go to the direct comparison because it probably
So
will end
it
up being that.
diverges because direct comparison test and summation of n from 1 approaching infinity. Yeah, I get it.
Okay. Now, the integral test, I guess, and alternating series. Alternating series, let's talk that one. That one's probably one of your somewhat easier ones. I mean, it's definitely easy to recognize. That's when you got your negative 1 to the n or n plus 1 times something else. But there's a few things you got to do with that. And the key there is the limit of your a sub n part, not including the negative 1 to the n, but the what's left over, that has to equal 0, which means it would converge. Now, if the limit does not equal 0, then you're not really using the alternating series. What you would end up using is your quickie test, because the limit does not equal 0, whether it's with the negative 1 to the n or not. Okay. If the limit of a sub n does not equal 0, then with the negative 1 to the n times a sub n, it's definitely not going to equal 0. The limit's not going to exist because it'll bounce back and forth. If this limit would equal 1/2, then the quickie test would say, well, it bounces back between negative 1/2 and positive 1/2, so the limit does not exist, which is taken care of by the nth term test. Yeah.
You can use the sine cosine for alternating series too, right?
Yeah, some of the combinations with sine and cosine actually turn out to be alternating. So you gotta, once in a while, you gotta write out a few terms to recognize that. But yeah, the sine of, what was it, pi over 2n, I think that would end up being alternating. Would that be the one? Not sine, yeah. Cosine of pi n would also be alternating. Cosine of 0 is 1, cosine of pi is negative 1, 2 pi would be back to 1. So yeah, once in a while the alternating is kind of masked with the cosine or sine, but with the right combination, it fits that. So keep that in mind as well. Then the integral, well, I would say most of the series could be done a lot easier using something else. But there's a few that fit nicely into the integral test. Especially with some substitutions that you can do. Sometimes the integral test is the best approach. Although, I mean, pretty much you could use the comparison test for anything if you get all the conditions met right. In some cases that would take quite a bit to get them right, but maybe the integral test might be easier in those cases. But a lot of times the integral test, it's doable, it's just long and drawn out. But sometimes that's the best choice. So you need to decide which ones you like the best, check for those. Then as you kind of go through all the options, oh, I'm down to this one, I've got to do it, so just do it. So, sometimes you got to do the one that you don't like to do, just because it will work out the best. But that's what I would do, is go through on your sheet of paper, list out all of the tests and list all the details. We can use this test if such and such, and a lot of them have just one or two conditions to meet. A couple of them have a few more you got to make sure you show, but definitely if it fits a P-series, use that. Although integral test would also work on those. It'd be the really long way around it, but the integral test basically is used to prove the P-series test. But so any particular questions? Oh, this will be the bulk of the test, but then 9.5, when we looked at the alternating series, we went above and beyond just saying it's convergent or divergent. So let's take a look at those in particular. Alternating series, well, they can diverge. The series diverges, converges conditionally, or converges absolutely. Absolutely. Now that's the next step up. The easiest example here, of course this probably won't be the one on the test, but just to illustrate what this is meaning, converges absolutely. Well, that would be if we can take the absolute value of the series. Of course, this one where it's the alternating part, that's just going to end up being our 1 over n. Well, the series of 1 over n does what? Okay, that diverges by what test?
P-series.
We can use P-series on that. Okay. So it's this original one will not converge absolutely. It will either diverge or converge conditionally. So the first thing I would do is go ahead and look at the absolute value of it, work with just the a sub n part. If that converges, then automatically we can say it converges absolutely. But if it diverges, then we got to go back to the original and say, okay, the absolute value diverged. Now let's look at how we can work with this one. And usually what ends up working is the alternating series test. It fits all the conditions, and all we have to do is show the limit equals what? Okay. So since the limit of our a sub n term equals 0, what do we end up with? It converges by the alternating series, so we say this series will converge conditionally.
And that's only going to be for the alternating series?
Yeah, that'll happen with alternating series. Okay, so that's kind of the last part. We kind of look at converge or diverge, and then we take it one step farther. Well, does it converge absolutely or converge conditionally? If it converges, still may just diverge. And if it diverges, it just diverges. There's nothing else we can say about it. Thank goodness. Okay, so 13 problems. Not a lot of problems, but there's plenty to look at in it. Any questions?